Welcome to CS 1401, video 5.1, about implementing our pseudocode solutions in a programming language. So the important concept for this course is that we're going to design solutions for information problems regardless of the way in which we implement it. The idea is to solve the fundamental problem, address the fundamental factors of the problem. Then we take our solution and we implement it in a computer language. Let's take a look at a couple of examples just to start to see what I'm talking about. Here, for instance, is a pseudocode algorithm that's very simple. It's one in which all the program does is display the message, welcome to CS 1401. So my algorithm is called welcome, and all I do is give the user the output, welcome to CS 1401, which is, of course, heartfelt. Well, if that's the pseudocode algorithm, what does it look like in Java? Well, here's the entire Java program. So there's a keyword called class, and you'll learn more about that later. The name of our application, our program, is welcome app, which I mean an app for saying welcome. And then, like every Java program, it starts with a kind of formulaic set of symbols. And I'll talk a little bit about what those mean, but we're not going to be focusing on that precisely right now. But we can think of it as a kind of thing we have to say to make our program work, and we'll learn more about how that works later on. Suffice it to say that public means that our program is going to be able to be called from anywhere. Static means that it doesn't belong to a particular kind of object, and we'll look at data types a little bit later. Void means that the program called main returns no value, it just does something. Main is the name of a function, and main is a special name of a function because it's the start of the program. String means that it takes an array of string for arguments, but in fact there are no arguments, and args is just sort of a placeholder here. As I said, we don't have to pay too much attention to this point because we're not taking any arguments in, but suffice it to say that the name of our program is welcome app, and it runs by calling a function called main, which is our the main part of the program. Well, let's look at the body of the program now. It says system.out.println, that's what that means, and then there's a message in double quotes, and it's terminated by a semicolon, which means that's the end of the statement. So the whole body of the program, which corresponds to our one statement in pseudocode, is we ask the system to print out the line, welcome to CS 1401, and then there are a couple of closed brackets which basically indicate that our program is over. So that's the entire program. You can see that when we translated it from pseudocode to Java, we had to add a bunch of extra things to make it run. And as we program more in Java, you'll feel more comfortable with that, and you'll be able to get the idea right away. Now, in Prolog, the program looks really different. So here's the entirety of a program which I wrote called welcome.pl, which stands for Prolog. Colon dash symbol at the start of the statement is a Prolog symbol that means that this is unconditional. Just try to prove the right-hand side of this expression, everything after the colon dash. And how do you prove it? Well, in our case, you do that by executing this predicate called writeLine. And what it does is it writes out to the terminal everything between the two single quotes. Now, the statement ends with a period, so that's different from Java. And also you'll notice that the text we want to print out is between single quotes rather than double quotes. And that's just one of the differences between Prolog and Java in terms of handling simple output. Next, let's run our two programs and see if they work. So first, I'll open up a terminal and I'll call the Java compiler, javac, and apply it to welcomeapp.java. And then when we run the Java app welcome app, it prints out welcome to CS 1401, which is exactly what we expected. Let's try running our welcome app in Prolog. So I bring up the SWI Prolog terminal, and I'll enter the loading of our welcome program, and I do that by typing in left square bracket the name of my program and right square bracket, then a period, and then I hit return. And sure enough, it prints out welcome to CS 1401. And then it says true, because remember that what Prolog does is tell us if something is true or false, and it was true that it was able to print out CS 1401. So that's our first algorithm in both represented in both Java and then in Prolog. Let's take a look at another algorithm that we already know, which is how to calculate body mass index. So here's the pseudocode algorithm we developed before. And let's take a look at how we might implement this in Java. So here's the Java program. Now, the first statement says import java.util.scanner, and what that is asking the Java system to include in the functions available to us a set of utilities called scanner that are useful for getting input from the user. Well, our program is going to be called Calculate BMI app. In other words, it's an app for calculating BMI. Again, there's this formal start with public static void. Again, the main body of our program is called main, and in this case, that's the only part of the program we've got. And again, there are no arguments. The first thing we're going to do is create a scanner object, which is going to let us get input from the user. So I'll create something called in, an object called in of type scanner, and that's going to be a new scanner. Next, we're going to prompt the user to type in his or her weight in pounds. So I'll write system.out.print and then a little text, enter weight in pounds, colon, and I've got a space after the colon before the ending double quotation mark so that it looks pretty when the text is printed out. Next, we'll set up a new variable called weight, and it's going to be an integer, and I'll talk in another class about what that means. We'll call the scanner and ask it to input the next integer entered by the user. Next, we'll print out a prompt for the height, then we'll get that using the scanner again. Our next statement is going to be to calculate BMI, and there our BMI is going to be a number with a decimal point in it, so it's called a float. And the reason I have float in parentheses there is because we just input some integers, and I need to convert my integers to floats, and I'll talk about that a little bit later too. And then finally, we'll print out the text, your body mass index is, followed by the body mass index, and that's our program. So it's fairly complicated for such a simple program in the sense that we have to include this utility called the scanner, and we have to create a new scanner, and I've got to call system.out.print and so forth, and I need to declare my kinds of variables, and including ints and floats and so forth. But that's the way Java worked. It's a typed language. In contrast, let's take a look at how the Prolog program works. Now, Prolog, as we know, is, in contrast to Java's imperative style, a logic programming language. And the code looks a lot simpler here. Again, it starts with this colon dash, which means basically try to prove everything on the right, which for our purposes at this point means do what's on the right, or do the right thing, I suppose. And so the first thing we'll do is write enter weight in pounds, And again, our text is going to be delimited by single quotes, and you'll notice there's a nice space after the colon to make things look pretty. Then we just say read weight, and weight is a variable, and it starts, as do all Prolog variables, with a capital letter. Then we'll write the next prompt for height. We'll read height. I will calculate body mass index, and the is our assignment operator. So BMI is, and then this calculation on the right. And then I'll write out your body mass index is, and on the same line, it'll write BMI and then end that with a new line. And that's the entire program. Now let's try running our body mass index program both in Java and in Prolog. So first in Java. So let's go back to the terminal, and I will compile the BMI app in Java, and it compiles. And then I call the app, and just like last time, it prompts me for the weight in pounds, my height in inches, and enters my body mass index, or gives me back my body mass index, and terminates. So that works great. Let's try the same thing in Prolog. So I load the Prolog program calculate BMI, and it, just as we expected, prints out enter weight in pounds. Now here I enter my weight as 174, and I put a period after that, which is something I have to do when I use read in Prolog to tell Prolog that it's the end of the input, sort of like entering a pound sign on the phone after you've entered a number. Well, then it prompts me for my height in inches. I enter 72 and period, and when I hit return, it prints out your body mass index is 23 point something and says true. So that works too. It's true that for these simple examples, I was able to translate our pseudocode algorithms into both Java and Prolog fairly straightforwardly. But it's also true that different languages are typically used for different kinds of problems. For instance, Java is a very capable language suitable for lots of mathematical calculations, lots of user interface interaction, graphics, and so forth. Whereas Prolog is for artificial intelligence and is used to prove logical things. For example, here's a Java program written by somebody else that calculates and shows fractals, which are geometric figures. Here's the program, and here's what the program's output looks like. That would be really difficult to do in Prolog. On the other hand, here's something that's going to be easy to do in Prolog, but would be difficult in Java. So in logic, a syllogism is something like A implies B, A is true, and therefore B must be true. So here's a Prolog program, and I'll define some things that are true, namely that Spike is a dog and Fluffy is a dragon, that something is mortal if it's a dog, that something's immortal if it's a dragon, and it's also true that something is cynical if it's immortal. I've loaded this Prolog syllogism program into SWI Prolog, and let's see how it works. First, let's see if Spike is a dog. So I'll type in dog Spike, hit return, and sure enough, it says that's true, and that is true, of course, because it's in our program. Next, let's see if there's any dragon out there. So I'll type in dragon x, where x starts with a capital letter, so it's a variable. And what Prolog will do is try to find a case that makes dragon x true by finding a value for x. And when I hit return, it says, sure enough, x equals Fluffy. So that works. Now let's try and see if we can find something that isn't true. So I'll type in dragon Tim and hit return. And sure enough, Prolog tells me that dragon Tim is false. It's not part of the knowledge which I entered into my program. Now let's try to see if the syllogism part works. So remember that all dogs are mortal. So I will type in mortal Spike, because Spike is the name of the dog, hit return, and sure enough, it says true. So it was able to properly work through the syllogism. Similarly, let's see if the dragon Fluffy is mortal, and no, Fluffy is immortal. It's a dragon, it's immortal, it's false. Next, let's check to see if Fluffy, our immortal dragon, is mortal. And when I type in mortal Fluffy, Prolog is unable to prove that's true and correctly returns false. In fact, Fluffy is immortal, so when I type in immortal Fluffy, that comes back true. Finally, let's test out another syllogism, this one nested. So let's see if there's anything that's cynical. Okay, so let's think about it. Something's cynical if it's immortal. Something's immortal if it's a dragon. We know there's a dragon called Fluffy, which means there's something immortal called Fluffy, which means there's something cynical called Fluffy, and sure enough, Prolog returns x equals Fluffy, which is exactly what we expected. So these two different examples, the fractal and the syllogism, show how two different kinds of programming languages are appropriate for different kinds of problems. That's pretty much the end of this video. In the next video, I'll talk a little bit more about variables and states. See you then.